Hello and welcome to our discussion today. This is on operating systems and we are looking at CPU scheduling. When we are talking about CPU scheduling, normally we are looking at the operating system, which is the one managing the resources available for a computer. And when it is managing processes for a computer or resources for a computer, then it has to manage this resource we call the processor, that is the CPU. And when we are talking about scheduling, by definition, it refers to the process that allows one process. And this is where I would like to take you back to the lecture where we talked about different processes. And when you're looking at different processes, they are normally classified as follows, whereby you would have processes that are running or processes that are accessing the CPU. Others are not accessing the CPU because of one reason or another. And if I could just take you back to the lecture where we talked about process creation, normally in an operating system, there is the process where we talk about a task. So a process is a task and it is an execution of an individual program that can be traced, and it is going to have the data that is being worked on as well as the instructions that are working on the data. So normally that is what we call a process, and that is the one which is taking place inside the processor. And we looked at the different processes where you could have process A, process B, process C, and then the program counter, which is containing the instruction of the next process that is going to get into the processor. And this is all located in the main memory. So that is how processes operate. Here, this is just a trace of process A, where it started and how it is going, process B as well, and process C. They are normally given IDs and then they would now begin to move. The ID is normally the starting address of a program or the process until where it ends. So that is how they move. And normally, in the traditional systems, they are used to have two-stage process model whereby a process could either be running or not running. If it is not running, it is waiting to get into the CPU. If it is running, it is already in the CPU. And this is how a not running process is put in a queue. So the processor is here, whereby the process is in a queue and it will enter into the queue. Then it is dispatched to the processor when it has all the resources that it needs, and then it is worked on and it is released. So a process is created when a batch job is submitted, and once it has been submitted, then user can log on, and then it is created to provide a service such as printing or any other process we can talk about. It is normally terminated if there is a halt instruction, and a halt instruction, it could come in form of many reasons. We talked about interrupts. That is one of the reasons you could have an halt instruction, whereby maybe an error has occurred or a process of a higher priority has come into the processor, and that could maybe halt. Either the user logs off or you quit the program, that is the application, or an error like we have talked about. So that is how processes are terminated. The reasons is it could be it has completed normally, or the time allocated has exited, or memory is unavailable, bounds violation, protection error, arithmetic error, a time overrun. All of those are reasons why processes could be terminated. And so, and even these ones where we're talking about input output failure, invalid instructions, privileged instructions, data misuse. So this is part of what we had covered. And the processes are normally in five-state model, where it could be running, it could be ready, it could be blocked, it could be new, or it is exiting the processor. So that is how processes are normally classified, or the states of a process are normally classified. So it is normally, this is the traditional view of how process look like. You could create a new process here as a user or as the application program that is performing different activities. Then it will be admitted into the queue where it is ready for processing. Then within this queue, it can be dispatched into the processor where now it can be worked on or the data processing activity can take place. If there is no interrupt or there is no any of those reasons we have mentioned, then it will be released. After it has been worked on, it will be released and there will no more termination occurs. So you exit. If there was something that has happened, maybe it requires some maybe input output, or it requires some event to occur, then it means that it is going to go to the blocked state so that it waits for that event to occur, or it waits for that input output component to be available so that it can continue with its operation. So that is something which we had covered, and I felt it is important that you look at it just to understand how normally processes occur inside the processor. Because the CPU or the processor is what we are looking at, and we would like to understand it in that perspective, whereby we have created a process, and now it needs to get into the CPU. The CPU is just one, and it operates traditionally, whereby it is one instruction at a time. And that is why we are saying that when one process is inside the CPU, it will have to wait for the CPU while that execution is taking place until it is finished or any other reason like we have listed occurs, and then it can be allowed into the CPU. That is why we are talking about scheduling being a process of determining determining which process will own the CPU for execution, while another process is on hold. So basically, that is what it means by CPU scheduling. So the main task of CPU scheduling is to make sure that whenever the CPU is idle, the operating system is going to select another process to take hold of that CPU. So the main idea is that the CPU is kept busy at all time. Is kept busy is kept busy at all time, so that whenever there is no process or a process is waiting for some other activity to take place or is waiting for input output to happen, then it can be running another process. So the selection process will be carried out by the CPU scheduler. So all of these activities are being done by the CPU scheduler. Is the one which is doing the selection of which process is going to be carried out or which process is going to get into the CPU for execution, and it selects one of the processes in memory, like we have shown in the other presentation, that all these processes, and when we are talking of processes, imagine that you have loaded maybe a Word program. You have also started maybe a Google application, that is Gmail. So you are writing an email and you would like to send it. So that send activity will have to take hold of the CPU. The moment you have sent your email, it means that that process is out of the CPU. Instead of the CPU staying idle, then another process can be taken over, and you had a Word document that you were editing, and those changes need to be executed. Then those ones will take place in the processor or in the CPU. So the work of the CPU scheduler is to select different processes or different data execution activities that are ready for execution from main memory. So all the programs that are loaded into main memory will always queue their activities on the registers that we discussed in our previous class. So it could be the program counter to show which instruction is following next, and it could be the address registers which are showing the addresses of the data that needs to be worked on. So once they are on the scheduler, then whenever the CPU is idle or is ready to take another instruction, then the scheduler pushes them into the CPU. That is why we have this diagram whereby we are talking about the different process states, whereby a process will be created. Well, let's say, for example, you are finished working on your Word document and you would like to print it. So that print process will be created, then it will be put in a queue so that it is in the ready state. It is in the queue waiting for the processor to be ready. We will see the different scheduling algorithms which are used by the CPU scheduler because they are different depending on the type of CPU and the architecture on which the computer is built. So up to there, I hope we are together, Juma and Joseph. Okay, hopefully you are able to hear me so that I am not talking by myself. And let us move on. So when the process is in the ready state, whenever the CPU is ready or is idle, then the process will be dispatched depending on the scheduler and depending on the scheduling algorithm that is in use. Then it is possible now to be pushed into the CPU so that it is executed. So that is how the process works. If there is no interruption at all, then it will be released. Maybe the print job has finished and it is released to the out of the CPU. If there was an interrupt, maybe it requires some input output, or there is an interrupt that has occurred for one reason or another, then it will be put in the blocked state so that whenever the event has occurred, or the input output that was required, the resource which was required has been made available, then it can be taken back to the queue, which is in the ready state. So when we are doing this scheduling, we need to understand what is scheduling, which we have already done, and then we need to understand what is starvation, context switching, and preemption. We will also try to understand the different scheduling algorithms with the parameters that are involved, and then how you can measure the performance of different algorithms, and some sample results will be seen at the end of the lecture. So an operating system must always select which process is going for execution in some fashion, or some method has to be put into use so that you can be able to know which process is going to be executed and which one is not going to be executed at any one given time. That is what it means. So when we are talking about CPU scheduling, then it deals with the issue of deciding which process in the ready queue will be allocated to the CPU. And the selection process is carried out by different scheduling algorithms like we will see. So let us look at some of these concepts. When we are talking about CPU starvation, what does that mean? It is the situation where a process waits endlessly for the CPU attention, or it waits for a long time before it gets to use the CPU. Now that is starvation. And starved processes may never complete the designated tasks. We know there are those applications which you load and they take over the CPU. Sometimes even the machine can hang and they cause starvation. Then, what is context switching? Context switching is the aspect of the CPU being able to move from one process to another, so that one process is not going to hold the CPU for a long time, but the CPU is able to switch or move from one process to the other, so that another process that requires saving the state of the old process and loading the new state of the new process. So if you are able to save a process at a given point and then move to another one and then come back to this one later, that is called context switching. But then increased context switching, saying increased context switching may affect the performance of the CPU because the CPU might spend a lot of time switching between tasks than doing the tasks themselves. So context switching is allowed, but it is allowed for a specified period of time, or it is allowed for a given moment, or for several tasks, and then the normal operation can proceed. Then there is also another term called preemption. And when we are talking about preemption, then what do we mean? That is where CPU can remove or purge a process being served in favor of another process. If one process has stayed in the CPU for a long time, so that it doesn't starve the other processes, the CPU itself can purge or remove. This is the same as, say, talking of remove. Moving a process that has stayed in the CPU. Mostly it is those processes which stay for a long time, or a process is being favored than the one which is being executed, then it may be removed. And new processes may be favored due to a variety of reasons, such like higher priority, smaller execution time, etc. So those are the determining factors of why preemption can occur. And like we will see as we continue with the discussion, is that there are two types of preemption. There is what we call preemptive and non-preemptive. So let us look at the different scheduling algorithms which are normally used. And as we look into that, then we need to understand how, when a process is switching from running state to, just to get back to what we had discussed, as a process is switching and CPU scheduling take place under these four circumstances. This is something we need to note as we move. The types of schedulings, when we are looking at the types of scheduling, we are looking at them in terms of the decision. Scheduling decisions are determined by number one is when a process switches from running to waiting state. And here we are talking about maybe waiting for some IO request, for some input or input That is one of the reasons why scheduling may determine another process to come and be executed. We are also talking of when a process switches from running state to ready state. Running ready state, like when an interrupt occurs. So in the waiting state, maybe there was some kind of input output you are waiting. Maybe you are waiting for the printer to finish one printing job so that it can take over. But when a process is just removed because there was an interrupt, then it means it goes to the ready state altogether. Then there is also the scenario where a process will switch from waiting to the ready state to the ready state. Maybe after the completion of input output activity, and maybe the last one is when a process terminates or it is finished. So all of these they can determine when they can determine a scheduling decision to be made, like who is going next into the processor. So feel free to ask any question. If I move with a lot of speed or if there is something you may not have understood, just stop me. I will be able to stop and explain. But I hope there, I just came to that because of preemption. Why a process may be removed from the CPU for another one to take over the CPU. Those are the reasons why, and that is why we were going back to the process states. So those are some of the determining factors. So in the circumstances, there is no choice in terms of scheduling. If a process is removed from execution, then what it means is that there is going to be some scheduling activity to take place. And here are some of the scheduling algorithms that may be used. So we start with the first one, which we are calling the first in, first out, meaning that the first job that came into the queue is the first one that is going to be served. And then once it is out of the CPU, then the other one comes in. Then we have this other one, which talks about shortest job first. And this one means that the job which has the shortest processing time is the one that is going to be put into the CPU first, and then it is executed. And then there is also preemptive shortest job first. So there is one without preemption, there is one with preemption. We will get into the details of them, but just if I could explain. The one that has preemption, it means that if there was a job that was taking place, and maybe it is taking like 2 minutes, and then another job comes into the CPU, to the queue, and it is taking like maybe instead of 2 minutes, it is 1 minute. Then the one which is already running in the CPU will be removed in the favor of the one which has a shorter time. But here in this one, we are saying it has no preemption, meaning that whatever was running in the CPU will be removed, but then the next job that is to be coming to the CPU, it has to be the shortest in the list. But in this one, the one which is in the list, if it is shorter than the one which is being executed, then it is going to be favored to get into the CPU. So I hope that one is clear. Then there is also priority based without preemption, meaning that any job or any process that has a higher priority, and we talked about high priority processes, whereby we have processes that have higher priority, others have lower priority. High priority processes are those which are maybe have been timed. Maybe you have an antivirus program that needs to be hit at any given time. Simon, could you mute your mic? Thank you. So priority-based scheduling is whereby any job that has a higher priority is going to be allowed into the processor and it is executed without being preempted. Whether another job that comes as a higher priority, it will have to wait for the one that is inside the processor to finish execution. Then there is preemptive priority base, whereby now priority takes higher consideration, such that even if the job that was being executed had priority and a new one comes in and it has a higher priority, then it will remove the one which is there. Then we have the round robin. When we are talking about round robin, it means that within the CPU, each process is going to be assigned a fixed time and it is in a cyclic way. So you could have like maybe your CPU scheduler can always hold, let's say, 10 tasks or 10 processes, just giving an example. So those 10 processes are going to be put in a circular way, such that process 1 is given maybe 10 microsecond, process 2 is given another 10 microsecond, process 3 10 microseconds, and they have that circular operation. So even if process 1 needed like 1 minute, it will run for 10 microseconds, and then once those microseconds are over, it is removed from the CPU, the next job comes in. And that cycle will continue like that until each one has had its time at the CPU or is finished with execution. And then there is the multi-level feedback queue. So when we are looking at multi-level feedback queue, here we are talking about a process whereby the queue, we are talking about processes which are in the ready state at that time. So the queue is going to be divided into different classes, whereby there is that class of high priority processes. There is also another class of the normal processes which don't need higher priority. And through that classification, then processes be taken into the CPU. Or they can use another classification of maybe processes that are similar so that they can be put into a batch. So it is all about having different classification. It could be classification in terms of priority. It could be classification based on the type so that you can have batch processes, or you can have interactive processes which require maybe some input output, and that way then you have listed the different priorities or the different levels of processes that are in the queue. So I hope all of those different scheduling algorithms which are used by the processor do make sense. Then we move on to where there is a scenario of mixing different scheduling algorithms. Processes and their parameters then can be calculated so that you can have certain performance measures, whereby you can have a set of processes that are going to give you the best performance in terms of the parameters that you are selecting for the activities that are coming into the CPU. So let's have an example here, and we have a process mix whereby process 1, process 2, 3, 4, 5 are on the schedule, or they are in the ready queue. The arrival time of each one of them has been given there, and like this one arrived at 0 time, the other one is at after 2 seconds, the other one maybe after 4 seconds, 8 seconds, 12 seconds, and so on. The priority, one has a higher priority, a lower priority. This one is 10, it's a bit lower. This one is 58, meaning that it is of a higher priority. This one is 40, middle level priority, and so on. Then the time it takes to execute, maybe this one takes maybe 10 microseconds, 1 microsecond, 2 microseconds, and all of that. So that is the chart showing the different process mix that we have. Different processes, different arrival times, different priorities, and different execution times. So when you have this kind of a mix, what happens? It means that you are going to select the specific mix using different scheduling algorithms that is going to give you the best performance. For example, if you were to take maybe process 1, which came in first. So using the first in, first out algorithm, it should be the one accessing the processor or the CPU. But it is going to take a lot of time there. So it is going to maybe delay the other processes which have a higher priority, like process 3, and it is taking less time. So that is where we have the process mix coming in. And we will see how that is done using this same example chart. So, like we have said, this is the simplest, the first in, first out, whereby the processes are served in the order in which they arrive, whereby you're going to take the timeline of arrival. So what is going to be used is the time of arrival in order to serve them using FIFO algorithm. So here it is. The one which arrived first is going to be served first, then like that as you continue. So the one which came in first is going to end after this duration of time. The one which came in second is going to end within a very short period of time. So imagine the delay that has taken place here between the arrival of the first one and the second one, but the second one has to wait until the first one has finished. So there is some kind of delay which happens with first in, first out. And that is what we want to reduce. Then we have P3 coming in, process number 3, and it comes in, but it has to wait again for process 1 and process 2 to complete. And there is also some delay which is taking place. And this is how you're going to calculate the performance measure, meaning that turnaround time for process 1 when we are using FIFO scheduling algorithm is going to be 10. Process 2 turnaround time is going to be 9 because it has come in like end time, how long it took, and the time of arrival. So it took 10 maybe seconds to execute, but it arrived at 0 seconds, so 10 seconds there. The second one came in at 11, but it goes into the processor at 11, but it takes 2 seconds, so the time is 9, the turnaround time. P3 has to get in at time 13, and it takes 4 seconds. So again, the time is 9. Duration, turnaround time again for program 4 After adding these 4 seconds for processing, it is at 17, and it takes 8, and that is 9 again. The same for 5, which is at 20, because you have to add the time it is taking, so that it is going to be 8. So when you add all these turnaround times, it's going to be 45 seconds, for instance, and the average turnaround time is going to be by the number of programs that are taking place, which is going to be 9. So the scheduling algorithm, that is FIFO, is going to be taking maybe 9. That is the total turnaround time. And the waiting time is also calculated by having the turnaround time minus the execution time. When we talk about turnaround time, is the time you came in and the long it has taken you to get, like, from the queue, once you were dispatched into the queue, and by the time you finish, how long it has taken you. But then waiting time is the time you are waiting on the queue, meaning that you're going to have the turnaround time, which is the total time from the time you got into the queue, and minus it with the execution time, the time it has taken you to be executed in the queue. So the process 1, it came at time 0, but the turnaround time it took is 10 seconds, for example, and its turnaround time was also 10, because that is the time it took for it to be executed. So it had a waiting time of 0, because it did not wait in the queue, it just went into the processor since it came first. The waiting time for process 2 is that it got in at 9, it took 1 second, so it is the execution time, the waiting time is 8 seconds. For 3, it got in again at 9. It took 2 seconds to be executed. So waiting time is 7. Same with 4, waiting time is 5. 5, the waiting time is 5. So you take the total waiting time, which is 25 seconds, and then the average waiting time, you divide it by the number of processes, which comes to 5. So in the FIFO, if we want to get the throughput or the performance of that FIFO scheduling algorithm, then we are going to say the number of processes is 5, the average time is 5, so it comes to 20, or the total time of completion, because we are talking about the average time being 5, so the total is going to be 20, so the throughput is going to be 5 divided by 20, which is going to be 0.5 maybe processes per unit time, which we are calling maybe seconds. I hope up to there we are clear. Okay, then we continue. What are the advantages? It is easy to understand and implement, but in terms of disadvantages, the average waiting time under FIFO is not minimal, and it may, thank you, Jean. I can see we are together. It may vary substantially if the process's execution time is going to vary. The CPU and device utilization is very low because at each one time you have to wait. That is why the CPU utilization will be low. Then it is also troublesome for time sharing systems, like we will see as we continue. Then we get into the shortest job first without preemption. We said preemption, whereby a process can be removed from the CPU if it has taken some time or if it is not of priority. So when you are talking about the shortest job first, it means that the CPU is going to choose the shortest job available in the queue, and then it executes it to completion. So if a shorter job arrives during processing, the CPU does not preempt, or it does not remove the current process in favor of the new process. That is what we mean by without preemption. And the timeline on the following slide should be able to give us that. So Let us say we have these 5 jobs in the queue. And when we have those 5 jobs in the queue, the CPU is going to check which job has the shortest time to complete. And that is the job that will get into the processor. And that is what we are seeing here. So let me show it here. Turnaround time for each one of these is, this one is going to be 10, 9, just like we had done in the previous one. But then, which job is the shortest? And that is why the time here is reducing. The shortest is the one that is going to be taken for execution. Like here, if we go back to our table. Yes, somebody has a question? Any question? Oh, maybe it is somebody who has their microphone on, so we can try. Yes, Jane, you have raised your hand.
I'm not understanding how you are the time like now you're talking about the shortest time.
Okay.
Kwa hiyo unatumia simu.
Oh, so I just came back to the table so that we can get a picture of what we are dealing with when we are dealing with the second scheduling algorithm. And here we can see process 1 is taking execution time of 10, let's say seconds. 2 is taking 1 second. 3 is taking 2 seconds. Maybe 4 is taking 4 seconds. And then 5 is taking 3 seconds. So that is the picture that we have. Now, let us go back to our algorithm again. Shortest job first without preemption. Yes, that is where we are. And here we are talking about now job 1 has arrived as the first one, but once it has arrived, it has to be checked against all these other jobs that have arrived. And since its processing time is going to be longer, then it will have to wait. Hapo tunaelewana? So, by principle, shortest job first will take job 2, which has the shortest processing time. And then it will follow it up with job 3. But remember, the one who came first is job 1. So it's the one who got into the processor. But then after that, job 2 continues. Then after that, job 3 is the one which takes over the processor and executes because it has shorter time compared to job 4 and job 5. Although when you are comparing job 4 and job 5 has a shorter time. That is why it has executed first and then job 4 comes as the last one. You have seen that. Jean? Okay, thank you. Yes, because since jobs come maybe one following the other, that is why job 1 was taken because there wasn't any other job to compare with. But then after that, job 2 was taken because it has a shorter time, then job 3, then job 5, before you get to job 4, process number 4. So that is where shortest job first now kicks in. And this is where we are calculating. And when you calculate the total turnaround time, it reduces. When you compare it with the first in, first out, we had turnaround time of 9. This one has reduced up to 8.8. Why? Because another job has been taken first. The one which has a shorter time to execute is taken first so that it can be executed and the CPU is free. And it goes on to show that even the execution time reduces again. The average waiting time is 4.8. The other one for first in, first out was around 5. So there is better performance compared to first in, first out. But the throughput is still the same because it is 0.25. But in terms of turnaround time and waiting time, there is an improvement in performance. Then we move on to the advantages and disadvantages of shortest job first without preemption. So it is optimal in that it gives the minimum average waiting time for a given set of processes. But since there is no way of knowing execution times, the same need to be estimated. This makes the implementation more complicated because again, you could not tell at the beginning of the first job. That is why it becomes complicated. And then it is also going to suffer from starvation because if, for example, you have many jobs that are very short and one long job, it may be starved because of waiting for these short jobs to be finished so that it can take over the processor or the CPU. That is why we are talking about now starvation coming in. Then we have shortest job first with preemption. And when we are talking about shortest job first with preemption, is that even if the first job started, but then another job came which has a shorter time, then the CPU is going to preempt or is going to remove the current process in favor of the new process that has a shorter time. So the execution times are compared by the time remaining and not the total execution time. So let's say again our job one, which was being executed and it is taking 10 seconds. And on the second second, then process number 2 came in and it is taking maybe 1 second. Then the first one will be removed because it still has a longer waiting time or a longer execution time remaining, and then the first one is taken over. That is what will be here. So program 1 was in execution, then ikakutwa na program 2 which has a shorter time. It was removed so that program 2 executes. Then program 1 again took over, but before it finished, program 3 came in, which also has a short time. It executed. Then as it took over again, program 4 came in, it has a shorter time. Then program 1 is removed so that program 4 executes. And then as you continue, program 5 comes in and it has a shorter time, then it takes over until it finishes, then program 1 can finish. So that is what is meant by preemptive shortest job time scheduling, whereby the shortest job which comes in is compared with the one which is executing. And this is what happens. You see, the average turnaround time has really reduced. Why? Because the turnaround time for job one, yes, it was 20. Why? Because it kept on being removed. So it ended at what time? At time 20. Maybe it took 20 seconds for it to complete. That is why we are talking about now the end time minus the time of arrival. It arrived at time 0, but it finished at time 20 seconds. That is why it is 20. But compared with 2, which came in at time number 3, and it took maybe 2 seconds. So the turnaround time was 1. This one came at time 6, then it took 4 seconds. So the turnaround time is 2. The other one finished at time 12, but it had come in at time 8, so it took 4 seconds. the turnaround time is 4 seconds, sorry. So that is how you are going to get the total turnaround time, which is 30 seconds once you add all these times, and then you divide by the 5 jobs, which gives you 6 seconds, for example. Then when you are talking about now the waiting time, see the waiting time has really reduced to 2, meaning that at any given time, the waiting time is going to be 2 seconds, because the one which was taking long was kept on being removed. So in terms of performance, it has really improved. Again, the throughput is the same, but the time duration has really reduced. So it reduces the minimum average waiting time for a given set of processes. So the waiting time has really reduced, but since there is no way of knowing the execution times, the same need to be estimated. This makes the implementation more complicated, and that is why you may not find it in current system implementations. Also, too much preemption may reduce in higher context switching, which we said it can affect the system performance because the CPU will now start doing a lot of context switching instead of doing the actual data execution. So that is something to be careful with. And again, like the non-preemptive counterpart, the scheme may suffer from possible starvation because if a process is taking a really long time and it keeps on being removed from the CPU, then it may be starved for a long time. Then there is also priority-based scheduling algorithm without preemption, whereby the job that highest priority is the one that will be put into the queue for execution. And if a higher priority job arrives during processes, the CPU does not preempt the current process in favor of the new process. And so this is how we are going to see them operating. So here, again, we will have the challenge of determining which one has a higher priority. Again, since we do not know which one has a higher priority, or we may not be able to determine, then it's just a matter of considering which one has the shortest time or which one is able to be finished first. So since all of them have the same priority, for example, process 1 will be executed first, followed by process 2, then process 4 comes in. Why? Because process 3 maybe hasn't arrived. Then process 5 and process 3 comes in. When you look at this, then the turnaround time increases. This is in terms of the turnaround time for process 1, process 2. See, for process 3, it has really gone up because maybe it wasn't of a higher priority. So it shoots up. It waits for a long period of time, and then process 4 and process 5. When you calculate also, the average waiting time increases, and when you look at the throughput, it's still the same, but in terms of advantages and disadvantages, performance measures in priority scheme, they have no meaning that you are not interested in how the CPU is going to save on time or execution speed, but you are interested in jobs being executed, that is all. And so the major problem with this algorithm is that there is indefinite blocking or starvation because if a process is not of a higher priority, then it may be blocked for a long duration of time. Then we have priority based with preemption, whereby if there was a job that is of priority being executed, but a higher priority process comes into the CPU will remove the current process in favor of the new process. And so this is how it works. So let's say program 1 or process 1 was executing, but then another one comes in and it is of a higher process. It will be executed. Then Process 1 again continues. Then process 4 comes in. It is of a higher priority. It is executed. Then another one comes in. It is of a higher priority than 4. It is executed. Then 4 continues until you get the last one. So again, this is how the performance measures will look like, and you can compare them to see how they differ from one another. And if you look at the throughput, it's still the same, but in terms of advantages and disadvantages, is that performance measure in priority scheme still has no meaning. It is all about what is the priority. But in terms of challenges, is that the algorithm can also bring about indefinite blocking or starvation, because if a process is not of a high priority, then we shall have a problem. Then too much preemption may result in higher context switching, and this affects the system performance at the end of the day. Then we have round robin, where we said that each process is going to be given a predetermined time slot. So, like we were saying, each one of them can be given maybe 2 seconds or whatever it is. And so, when that slot comes into play, then it has a FIFO behavior, and very small time slots can also can also result in high context switching, and that can decrease performance. So let's say each one of them is going to be given what? Maybe a particular duration of time. And here we can see that a particular duration of time has been issued, which is like 2. So if process 1 did not complete within these 2 seconds, it is switched out of the CPU, and then process 2 takes over, it finishes its execution, then program 2 process 1 again comes back, but it did not finish within the 2 seconds again, then it is pushed out of the processor, and process 3 comes in, it does its work. If it has not finished, it will be pushed out, but here it has finished, so it completes, and then process 1 continues again. Then if it has not finished again, process 4 comes in, like that. So that fixed duration of time is the one which determines which process is taking over the CPU. And like you can see, the average turnaround time has reduced in comparison to the priority-based algorithms. And also the average waiting time has also reduced in comparison to the priority-based algorithms, but the throughput is the same. In terms of advantages, it is a bit fair compared to the others, and the performance of the scheme depends on the size of the time given. So the time quantum is the one which is going to determine how the performance will be. And if the context switch time is about 10% of the time quantum, then about 10% of the CPU time will be spent in context switching. And that can be an advantage or a disadvantage depending on how we look at it. And so when we look at these scheduling algorithms, you can see the different average waiting times. The throughput is the same in all of them, but the turnaround time and waiting time has been varying a lot. And if you can look at it properly, you will see that the shortest job first with preemption and round robin time are the ones which have better performance when it comes to average time and average turnaround time. So that is how you can compare them, and you see the ones which are better. So the preemptive counterparts perform better and the turnaround time. But FIVO and round robin ensure there is no starvation, so that each process is going to have its time in the CPU. However, they might suffer from poor performance. So that is something that you need to be at the lookout for. But the performance on round robin is dependent on the time slot value. So if you find that shorter time slots are a disadvantage, then the time slots can be increased, and that will have solved the problem. So this is how you can have round robin algorithm with context switching, whereby at this point there is switching which takes place, at this point another switching takes place, and that is how switching happens with round robin. And this is how it is going to appear, the performance. So you can look at it in detail and see how it behaves. So the throughput will increase, the CPU utilization will also increase with the round robin algorithm. Actually, most of the time, the round robin is used in combination with fast in, fast out in the current systems that are working. And so still those are the comparisons. And then when we are looking at the performance measures for round robin algorithms without context switching, then context switching time is pure overload. So because the system doesn't do any useful work when switching, then it is better to just remove the context switching aspect, and then we work with the time quantum, which is large enough with respect to the context switching time. And what we need to be careful with is that we do not need to make it too big so that round robin it degenerates to FIFO. So that is where there is aspect of finding the optimal value of time that is going to work. Then we have the multi-level feedback queue algorithm. And in this one, we have a single process and single queue, which is applying the same scheduling algorithm. But with the multi-level, we are going to have multiple queues with different levels of priority and different scheduling algorithms. So this is an improvement of the traditional queuing algorithms, which now helps in addressing some of those issues. And like here, you can have system jobs which are in the first queue. Those which are computationally intense, they are put in the second queue. Those which are less intense are in the third queue, and those which require multimedia capabilities are put in the fourth queue. And then each queue can use its own scheduling algorithm. Like Q1 is round robin. Q2 is shortest job first with preemption. Then Q3 is priority based. And then Q4 is fast in, fast out. And with that, you are able now to be able to use the different algorithms and make the system more computationally performant. And so the different kinds of processes are assigned to queues with different scheduling algorithms. And the idea is to separate the processes with different CPU burst characteristics and their relative priorities. And here we see that the system jobs are assigned to the highest priority queue with round robin scheduling. On the other hand, multimedia tasks are assigned to the lowest priority queue. Moreover, the queue uses FIFO scheduling algorithm, which is well suited for processes with short CPU burst characteristics. And so that is how it works. And it has its own advantage. Where you have those multi-level feedback queues, it is very easy to prevent starvation. So that is one of the aspects we are trying to solve, whereby there is no starvation. And although it is not, it is the best, it is the most complicated, and it is actually the one which is used in most systems. And when we are looking at those many algorithms, they will use execution time of a process to determine what job is processed next. Since it is impossible to know the execution time of a process before it begins, then the value has to be estimated. And we normally use the alpha value so that we can measure the first degree filter to estimate the execution time of a process. And this is how it is obtained using this formula. So that is how you can be able to know which is the estimated time. And here, Z is the estimated execution time, T is the actual time, alpha will be the first degree filter, and then it has to be between 0 and 1. It has to be larger than 0 and less than 1. And so this is how you can use it for those different processes, and you apply the formula to determine the time, the duration, where we are talking about Z is the estimated execution time and T is the actual time. So those are the values we are going to use to determine the execution time. And so that is how it is calculated. You can look at it, and it has been given with an example here and how it operates. So I will leave this one for you to look at, but those are the different scheduling algorithms which are normally used in the CPU scheduling operating system. Round robin, FIFO, preemptive and non-preemptive, those are the parameters which are going to be used. So any question up to there?